Here begins the unit on circular motion. Start with lesson 31, and for the first part of this lesson, we're just going to watch a video. It's this one right here. We're going to watch a video online, and I'm just going to talk along with this video. It has the cheesy, rocky music in the background. Okay, I'm going to mute the music as classic as it is, no. And what is circular motion? Circular motion is uniform. Circular motion refers to the motion of objects traveling in a circle. Now, that doesn't have to mean a complete circle. Why are they showing this roller coaster? They're showing this roller coaster because anytime there's a curved piece of track, it represents a part of a circle. So when you're going on a roller coaster, there's all kinds of circular motion involved, even on the parts where you're not, going upside down in a circle or going around in a horizontal circle. So what's special about circular motion? And then the video just goes through some examples. So here's a guy doing the hammer toss or whatever that thing is. I think it's the hammer toss. Pretty incredible. And here we go. It's just this is just trying to give you some of the basics of circular motion. The radius r, the radius is from the center of the object to the path of the object is moving, and you notice that the velocity is always tangential to the circle. Tangent means touching, so it's a line that's touching the circle but not intersecting it. So I'm going to stop this a second. It says when the velocity changes, let's rewind that. It says, so the velocity is changing. So even though this circle may be going in a constant speed, like I'm spinning something with a constant speed, since its velocity is changing because its direction is changing. So by definition, anything going in a circular path is in a constant state of acceleration. If the velocity is changing, that's the definition for acceleration. So since the velocity is changing, the object is undergoing accelerated motion. So that's a very important concept. And the direction of that acceleration is something that you probably didn't think was true. The direction is, we got to stop it again, is always towards the center of the circle. Okay, so the direction of the acceleration is always accelerating towards the center of the circle, but its velocity is tangential to the circle, so it doesn't spiral into the center of the circle or just accelerate towards the center of the circle, because its velocity, it always wants to go straight. Newton's first law of motion. Everything wants to go at a constant velocity in a straight line. So it wants to go straight, but the string that's attached to it is keeping it going in a circular path, even though it's accelerating towards the center. So that's pretty important. And so we call this centripetal acceleration, or some people call it centripetal. And there's the formula. It's on your formula sheet that you have to know for centripetal acceleration. It's velocity squared divided by the radius. And it says the direction of the acceleration is also constantly changing. So the direction of the acceleration is always towards the center of the circle in circular motion. What causes the acceleration? Well, that depends on what you're talking about. In this case, what is causing this car to go around in a circular path? And the answer to that is obviously the friction. The friction of the tires on the road is causing it to go in a centripetal path, that combined with a normal force, because the force of friction is mu times Fn. So in this case, what's causing it to go in the circular path? As outlined here, the normal force of gravity, but really we're talking about the force of friction. So in horizontal circular motion problems, it's usually the centripetal force is usually the result of frictional force. Okay, and there we go. Oh, did I just miss something there? I think I did. Did we say the force? Yes, here we go. Here's another very important concept, FC. FC stands for centripetal force, and you can see the force, if it's accelerating towards the center, then the force must be towards the center. So the centripetal acceleration and the centripetal force are always towards the center of the circle. Continuing on, and then the video comes to Newton's second law. And we're just going to replace F with FC, which means centripetal force, and centripetal acceleration. The direction of the force is the same as the direction of the acceleration. Gone through that already. And if you don't know the velocity, then we have a way to calculate that. So, okay, let's stop it here. What's causing the centripetal force in this example? There is no string attached to the moon going around the Earth. It's obviously the gravity. So gravity is causing the centripetal force in this example here. That's the moon going around the Earth. Jerky there. Don't know how fast the moon is moving. So this is how fast. This is how we can calculate the velocity of the moon without having to get on the moon with an odometer. Here it is. Let me pause it there. Velocity equals distance over time. But when we're talking about circular motion, the distance is basically the circumference of the circle. And so we replace distance with 2 pi r, which is the circumference. And we also know that acceleration, centripetal acceleration, equals the velocity squared divided by the radius. Therefore, I can plug that into this formula here, and I get a new formula. The centripetal acceleration equals 2 pi squared over t. Now, what is t? Let's go back to this formula here. T is a value of time, but it's a very specific value of time. It is the period of revolution. So in other words, how long does it take the moon to go around the Earth? And there you get a new formula. That formula is also on your formula sheet. A new formula for centripetal acceleration. And then the rest of the video just goes showing some other examples, a lot of roller coasters. I think that's about it. It's all roller coasters. Yeah, okay, that's it. Okay, we'll stop this lesson here. And then in the next lesson, 31-2, we'll continue with circular motion.